Okay, last part of light is lenses, which is just mirrors really with glass. Yeah, I know mirrors have got glass in them as well, but the actual part of the mirror is the shiny bit at the back. These are actually just the shiny bits, the glass bits. Anyway, moving on. There are two types of lenses. Converging, which brings the light to a point, converge, and diverging, which takes them away from a point, diverge. They used to be called biconvex and biconcave, but those words have slipped into disuse as converging and diverging are far more descriptive. Just like the mirrors, the focal point is the point which is basically where all the light from a distant object focuses, or where all the light from a distant object appears to come from in a diverging lens. Basically, a lens is two refractions. Instead of refracting the light only once, it refracts it twice, as you see. Now, this seems to be a prism, but of course what it is the top half of a lens. This is not someone with a hat on. This is the other part of the lens. So it's just that part as illustration. And you can see it refracts at the surface going in and the surface coming out. And because of the arrangement of the angles of the sides, both of those bring it to a point over here, which will be the focal point of the lens. So, again, we have two ray diagrams. One ray passes straight through the optical centre. It's a little like the one that hits the pole and bounces back as if it was a plain mirror. This is like a plain piece of glass. It goes straight through the middle of the lens without deviating. Now, you know what I think about deviating. The other one is parallel to the principal axis, just like parallel to the principal axis in the mirror. And this one goes to the focal point, remembering that I did say, and I'm going to go on about it, that is not what actually happens. That's an illustration of what happens. Actually, you get refraction at both surfaces as it enters and leaves the glass. It doesn't do it in the middle. It does it at the change between the air and the glass, the border, the barrier, Right, so this is the first of the ray diagrams I want to illustrate for you. Again, you've got those two rays, one of them through the optical centre, one of them which is parallel to the principal axis and comes out through the focus. And where the rays really meet, that's where you get your image. That's the image. And because the rays are really meeting, it's a real image. As you can see, it's inverted, it's smaller, but it's real. And it can be projected onto a screen like any other real image. Now the object is outside 2f, twice the focal length, and it gives a smaller image. If we move it to 2f, we get a real image which is at the same size and the same distance as the other side of the lens. And if we move it inside, the image moves outside 2f on the other side of the lens, but still remains inverted and real, but now is magnified. So this can be used to magnify images and still keep them real, still have them projectable onto a screen. We have the same as we had with the mirrors. We have one setting where the image is at infinity and cannot be focused onto a screen or even our eye. This is when the object is placed at the focal point. Or we can have the image inside f. Now, when the image is inside f, what you're basically looking at is a virtual image. Again, because now the ray is going through f on the other side here, the rays are no longer converging but diverging. They're actually looking apart. Our eye is on the other side over here looking and is constructing this image here simply because it thinks the rays are coming from that point. As you can see, the image is upright and magnified. And this is the so-called use of a converging lens as a magnifying glass. The virtual image means, of course, you can't project this. Now, calculations again. Again, I'm going to urge you, remember that. My God, that's difficult to read in yellow, isn't it? Focal, oh my God, I can't read that. Focal length, object distance, V. Why did no one ever tell me that that was unreadable? Maybe it works better on the projector. Anyway, on this form, it's unreadable. That says focal length, U is object distance, V is image distance. Luckily, you've already done it in mirrors. This is actually called the lens maker's formula, and was discovered empirically, which means by experiment as opposed to theory. And has been in use for, well, hundreds of years. They haven't been making lenses that long. It's about 1450, something like that. I think Bacon, the English astronomer and philosopher who lived in about the 14th century, is reputed to have had a pair of spectacles, but it's one of those things we're never too sure about, things that happened that long ago. These people were cleverer than we thought, but it was the process of making pure glass without bubbles which had to come along before you could make lenses. So here is a worked out example. Again, I've done what I said. I've written the information down. I've written down the formula, and then I've put the numbers into the formula and just done the calculation. And because I've got a minus answer down here, of course it's 1 over, just like it's 1 over V, so we can turn it over and get the 120. The minus means that the answer must be virtual. This is because if you notice, the object here is placed inside the focal point. So we have the lens with the focal point here at 40, and the object must be placed there, meaning that it must give a virtual image. So the maths is helping us understand this. Here, magnification, as you can see, V over U again. There's the V, there's the U, comes up with the number 4. So the image is 4 times as large. It's magnified, just what we would expect. Right, measuring the focal length of a converging lens. Now, a converging lens works in exactly the same way as the mirror. You have the light box with the cross wires, which are essentially the object. The cross wires are the object. You have the lens and you have the screen, and you show U and V on the diagram. And if you're writing it up, you should really have this. You really should mention that U and V are measured with a meter stick. Every time you mention what you measure in physics, you should say what you measure it with. It's just good practice. Now, moving on to the eye, which, as you can see, also contains a lens. The lens of the eye is actually in 2 parts. You have the cornea, which is the first part of the lens, and the bit called the lens, which is the second part. Between them, they form one large lens. Now, the lens part of the eye is adjustable. The ciliary on either side pull the lens to make it thinner or fatter. The only other parts of the eye you need to know about are the pupil, which is the hole, the iris, which controls the size of the hole that the light can get through, and the retina, where all of the information is turned into electrical signals, which then go off to the brain. So accommodation uses just the lens part. The cornea itself, which is also part of the focusing ability of the eye, doesn't change. It's not changeable, but the lens is. By pulling at the ciliary muscles, you can change the thickness of this lens, and it can focus distant objects or close objects by changing the size and fatness of the lens. And this is called accommodation. You can simply take a distant object, make that thinner. I think definitely a colour change might be a good idea here. Let's try that again. There. Right, so a distant object, thinner lens, close object, fatter lens. And that's called accommodation, stretching that second part of the lens, the other part, so that you can focus onto the retina. Now, a diverging lens, which is the type that most short-sighted people like myself wear in their spectacles, this produces a virtual image. So I'm looking at a virtual world the entire time, Yeah, could be true. We could all be a hologram, blah, 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 blah. Anyway, a virtual image there. And again, because it's a diverging lens, the rays are diverging. So our eye, again, constructs the image from where it thinks it is, puts it there. There we are. That's the image, which is, as you can see, is smaller but erect, smaller and upright. So that is a virtual image, of course, because the rays don't actually meet. They only seem like they're meeting to our eye. And again, we can do the same calculation. The thing to remember, of course, is that F has to be negative. Why does F have to be negative? Because it's a diverging lens, just like a convex mirror, like a security mirror. The actual point, the focal length being used, is behind the mirror or on the wrong side of the lens. So we give it a minus figure. And we can use the same formula as before, but we have to remember to put in our minus down there at the bottom. And this minus, there we are, that's the minus going in down at the bottom, stays there because the other one is moved. That becomes minus because it's moved to the other side, and gives us minus 20 for V, which gives us, of course, a distance of 20, but a virtual image. And magnification is usually smaller. As you saw from the ray diagram, it has to be smaller. So this is called the sign convention. It's how we're able to use the same formula, the one at the top, the lens maker's formula, for all of these different types of apparatus. And all you have to remember really is the two on the left, which are the concave mirror and the converging lens, both have a positive focal length. Positive focal length. There we are. Whereas the two on the right, which is the convex mirror, the security mirror, and the diverging lens, my glasses, both have a negative focal length. Now this is negative in terms of when we're doing the calculation, not looking at it generally. It's a calculation one so that we can use the same formula. Because previously you would be given 4 different formulas for the 4 different things, and this always seemed to be very confusing. It's much easier if you just remember that a convex mirror has a negative focal length. From that, you ought to be able to extend to the fact that a convex mirror is like a diverging lens, and you're away, because they have virtually the same ray diagram. If you want to compare the two, you'll see what I mean. So, correcting vision. Well, I am myopic, I am short-sighted, so I need one of these diverging lenses, because the short-sighted refers to the fact that the image is focused short of my retina. It doesn't reach the retina. Now, this is usually called 90% of the time due to the fact that my eyes are too big. I simply have too big an eyeball. So, and that's my problem as most people's. There, the image is short of the retina. In order to get it onto the retina, there, we use this diverging lens, hopefully made better than that. That's a bit of a rough one, isn't it? It's going to give a rather an odd look of vision, that one is. Of course, when you get older, like myself also, you get long-sighted as well. Oh, what fun. So I am long-sighted and short-sighted now. And for that, I need this other type of lens. Now, they build them into the same glasses. That's what bifocal means. Long-sighted means that the would form behind the retina. And this is caused by the fact the lens just gets old and can't work as well anymore. So by adding this to help the lens, by adding a converging lens, we can bring it back onto the retina, focus on the retina, and that means that we can see again. I can see. Of course, underwater it doesn't work. This is one of the things which is very interesting. The reason this lady's wearing goggles, partly to stop the chlorine getting into her eyes, and except we all know it's not chlorine that's getting into her eyes, we just say chlorine because it sounds nicer. To stop it getting into her eyes, it's really so she can see. That's the real reason, really, I'd say. And that's because if you open your eyes underwater, the difference between the refractive index of the water and the refractive index of the cornea of your eye is virtually nothing. And it's not enough to refract the light. You see, the light doesn't refract. It keeps going on. It bends a little bit, but not enough to focus on the back of the retina. Now, normally, the refractive index of the air is 1 and the refractive index of our eye 1.4. That difference means we get bending. at the surface, bending at the junction. Whereas when we open our eyes underwater, there's no bending at the junction because there's no difference in the refractive index. The power of lenses. Now, if you go to the optician, he tells you how short-sighted you are. He gives you a whole number. And that's not the focal length. That's 1 over the focal length. It's a much easier thing to work with. And it's easier to work with because we often use lenses which are compound, which means they're added together. So, a focal length of 10 centimetres or 0.1 of a metre is written as 10. 1 over 0.1 is 10. So, for the same token, if you have 40 or 0.4, 1 over 0.4 is 2.5. Now, again, we use the sign convention so that we know which type of lens we want. A positive lens for reading glasses, for long-sighted people, has a positive number. So there you have P as to be plus 10. Whereas diverging lenses with, their negative focal length give a negative power as well. And that's the power that will be used to make a pair of glasses for a short-sighted person, minus 2.5. The most useful thing about this is the fact that often lenses are actually in contact. Lenses are put one on top of the other. Expensive cameras, expensive glasses using different types of glass, like such as mine, use two lenses which are in contact with each other, literally on top of each other. And when you have lenses in contact, you simply add up their powers. Now, adding up the power is a lot easier than working out anything else. So we work out the power of the two lenses and we add them. And this gives us a final power of the combination of lenses and, of course, therefore, a focal length. The minus signifies that the total effect of the lens, in this case, will be diverging. So, just to very briefly, if you're trying to correct a pair of eyes, and your eyes are 64, and the standard is 60, well, 60 minus 64 is minus 4. That means you're short-sighted. If you come up with a minus number, i.e. your power is greater than the power, it means you're going to have a short-sighted pair of glasses. You subtract, you get the minus 4. 1 over 4 is 0.25. That is the focal length of the diverging lens you need to correct your vision. So, subtract, turn it into a focal length. If the number is minus, that's a diverging lens. And this is the question. Absolutely no need to help you at all with this. Everything is in the PowerPoint. Off you go. That's the end of light. Next, forces.